So today we proved our two new limits. Sine x over x as x approaches 0 is 1. Cosine x minus 1 over x as x approaches 0 is 0. And we're going to use those to solve problems 39 and 41 from the text. So, you saw a brief flash of what 39 is, but we'll reveal it piece by piece. They're asking you to find the limit as x approaches 0 of tangent of 6x over sine of 2x. What I really want to try to make happen here is to have somewhere in my limit sine x over x. Or as we said in class, we could use the reciprocal of that. And the important thing here is that the input be the same as that x value. The input for sine be the same as that thing in the denominator, or in this case, the same as the numerator. So if we can make that happen in at least one place, possibly we can make it happen twice, we'll be able to solve this limit. What I want you to do is try on your own to rewrite tangent of 6x and perhaps multiply the whole fraction by something so that you do end up with either sine x over x or x over sine x. Right now we have a sine 2x. The 2x may not go away. Maybe we'll leave that there. And in that case, we would be looking for sine of 2x over x or 2x over sine of 2x. We might have to multiply by something. And remember, if you multiply the fraction by something, you must multiply both top and bottom by the same thing. So my suggestion is try somehow to get this 2x over sine 2x or sine 2x over 2x by doing some math, and split up your limit into two pieces at least. Give it a try, press pause, and I'll reveal step by step some of the work I did to solve this. So the first thing I did was I said, well, if I want 2x to be in the numerator or the denominator, I have to put it there. It's not there now. Right now I've got sine of 2x, but if I just want plain old 2x, I have to multiply both top and bottom by 2x. So I did, and I also split up my fraction. So I've got my 2x over 2x here, but I split it up in such a way that I actually have one of the things I was looking for, something we actually know the limit of. Remember, limits are distributable over multiplication, so this is going to help me find the limit of at least one piece of this pretty quickly. Press pause if you want to try some more on your own. So since I multiplied by 2x over 2x and split up my fraction into two pieces, I now have, like I said, we can distribute limits over multiplication. I have one piece that I already know the limit of, and that's 1. I still have to work on this second piece where I have tangent of 6x over 2x. And again, I'm going to split it up into things that maybe I already know the limit of. Right now, the two limits we know deal with sine and cosine. The cosine one deals with cosine x minus 1, and I don't have any addition or subtraction, so I'm going to keep trying to force tangent to look more like sine of something over something. Press pause if you want to try by yourself. So again, I'm just working on this last part of the limit because I've already gotten the first part, and 1 times anything is just itself, so I don't need to worry about the 1 anymore. I can just deal with this part of the limit. So I rewrote tangent as sine over cosine. Dividing by 2x is the same as multiplying by 1 over 2x. Nothing fancy, just rewrote tangent. So I now have sine of 6x over 2x. I got that from right here. But I don't want 2x, I need a 6x. Whatever's in my input for my sine has to be this expression down here. And it's not, so I'm going to have to fix that. And I'll worry about this other piece later. If you think you've got it, press pause and try on your own. So I multiply by 3 over 3, which is going to give me that nice 6x in the bottom. And again, I'll deal with this other piece with cosine in it later. Since the 3 in the numerator doesn't affect the limit of sine 6x over 6x, I can pull that out front here. Now I have a limit I know. I know the limit of sine 6x over 6x. So I end up with 3 times 1 for this piece. So I'm almost done with this tangent 6x over 2x part. This other part right here, is it okay to just plug in x equals 0? What happens when x equals 0? We get 1 over cosine of 0, which is just 1 over 1, and that's 1. So all the pieces we had before, remember that earlier we had a 1 times, and then we're going to multiply by these two limits. 3 times 1. So my whole limit overall, the limit as x approaches 0, of tangent 6x over sine 2x is just 3. Moving on to 41, we'll work that one the same way. So here again, I have a limit where I don't know what it is, but I'm going to try to split it up into pieces so that at least one of those pieces is a limit I do know, because that just equals 1. So what I did was, if I take my original and I multiply by 1 over x over 1 over x, I end up with this new limit. And now I have pieces that I know how to take the derivative of, or the limit of. Remember, limits are also distributable over division. It's one of the properties. So I have a limit in the numerator I know, that's just 1, and I can work from there. If you want to try on your own at this point, give it a shot. You probably can find the limit of this denominator all by yourself. Press pause, give it a try. Okay, so I'm just working on that denominator again. Keep in mind that we really have 1 over this. So I rewrote it as x over x plus tangent over x. X over x is just 1. And tangent of x over x is sine over cosine over x. And I can split that up as well. Dividing by something, if I take sine x over cosine x, and I divide by x, it's the same as multiplying by 1 over x. Rearranging the multiplication a little bit, I get this. And notice again, we have a limit we know. If we plug in x equals 0 to this part, we just get 1 over 1 as well. So I have 1 times 1 in this part of the limit. So to put it all together, remember I had 1 over this stuff, 1 plus 1 times 1. So I get 1/2 as my final answer for the limit to 41. So now we're going to practice a little derivatives of trigonometric functions. Basic 6 trigonometric functions, you need to get those derivatives stuck in your head so that you can quickly and easily take the derivative of these different functions. In number 1, I have 2 pieces. I can take the derivative separately of each one of those pieces. The derivative of sine is cosine. The derivative of cotangent is negative cosecant squared. In the second problem, I have secant and 1 plus secant x. We're going to have to use the quotient rule here, or you could try rewriting this expression. I'm going to go with quotient rule. Press pause, try this on your own. So here I took the derivative of low d high. So this is just low, just the bottom, and this is the derivative of the top. And then we have high, that's just the top, and the derivative of the bottom, all over low squared.
I'll just read out here.
I can simplify this a little bit further.
Oh.
And if I put the terms together in this way, you'll see that things cancel nicely, and we're just left with secant x, tangent x, all over 1 plus secant squared x. Sorry, secant x quantity squared. Here we have an e to the x. We actually have 3 functions in a row. So I'm going to have to really carefully use power rule twice. It's going to be an embedded power rule. Give it a try. Ooh, not power rule, product rule, product rule. Try product rule. You need to do it twice. Be careful how you do it. You might want to consider these two to be one term, or you might want to consider these two to be a term. Just very carefully take the derivative using product rule. You'll have to do it twice. Press pause, give it a try. So here I've taken the derivative. I have first times the derivative of the last, which is first. So I've got derivative of e to the x times the last, e to the x times the derivative of the last, plus this last part times the derivative of x with respect to x, which is just 1. And that's why you don't see it. You can simplify this a little by combining some like terms. Actually, there aren't any like terms, so don't simplify it. You can leave it just like this. So we still need to find equations of tangent lines, but now we're using trig functions, and your x input will always be in radians from me, most likely on the AP exam, also in radians. So if we're trying to find the equation of the line tangent, I need to find y prime first. Go ahead and do that, and see if you can write the equation of the tangent line at the point pi over 3, comma 2. Press pause, give it a try. So here I have the derivative at pi over 3. Remember, that's Leibniz's notation, which means derivative, and then here's the value I want you to take the derivative at. Derivative of secant is secant tangent, and I've put in my x value to get out the y value. We still have to write the equation of the line tangent. So I'm going to use my slope here in the equation, and here's my y1 and my x1. Okay, so on to the new material for today's lesson. We're going to actually do what's called the chain rule. We're not going to derive the chain rule or prove the chain rule. We're just going to say what it is. So if I have an embedded function, a composition of functions, and I want to take the derivative of that function with respect to x, the way it works is you take the derivative of the outside function with the inside function still in it, but then you take the derivative of the inside function. And then the important thing is you stop. Very important to stop. So here's an example of using the chain rule. If my function is sine of x to the 4th, I could use trig IDs and expand this, but we can also use this new idea of the chain rule, of taking the derivative of the outside function and then multiplying by the derivative of the inside function. My outside function, f in this case, is just sine. My inside function, g, in this case, is x to the 4th. So I'm going to take the derivative of sine